Where are we? Where are we? All right, probability. Technically our last topic of year 11. So once we finish off this, we're done. What we're doing each week, starting from today, you guys are going to be doing an exam a week. So by the time you guys come up to your trial HSC, I mean, all the year 12s that I've got, by the time you come to your prelims, you are obviously revising all of your topics, and at the same time, you've done enough exam papers to be ready for exam setting questions. All right, probability. This should be pretty straightforward. Most of it, topic 1 of probability, most of it's just your year 9 and year 10 probability. So there shouldn't be anything too crazy in here. That's the good news. So let's start. I think we already know that to find the probability is the number of outcomes that produce it over the sample space or how many you have. So we just start straight away with a HSC question. A packet contains 12 red, 8 green, 7 yellow, 3 black. 1 jelly bean is selected from packet at random. What is the probability that the selected jelly bean is red or yellow? So the idea is what you're going to learn is if you've got an or, that's a plus, right? Because you're allowed to get a red or a yellow. So 12 plus 7. So the probability of red or yellow equals 12 plus 7, which is 19, over, I think you already know, you add up everything. So what's this? 20, 30. Pretty easy. Any questions? All right, so you guys understand, as I said, probability, topic 1, is going to be pretty easy, and that's the easiest 2 marks you're ever going to get. So a student is chosen at random from the school's population. The probability that a student's name will begin with Q is 1 out of 26. Discuss this statement. Is this correct? So a student is chosen at random from the school's population. The probability that a student's name will begin with Q is 1 out of 26. What do we think? So is the probability of me picking a student with L 1 out of 26 in a school?
No.
No, why?
Because L may or may not be a common.
Correct. It might be there, it might not be there. Yeah, you don't know what the sample space is. You don't know the sample space. What if I told you there was only 5 people in the school? Think of that. Are you still going to say, oh, the Q is 1 out of 26? How does that make any sense? There's only 5 people in the school.
Yeah.
So you got to be careful with little things like that. All right. That one should be easy. That one, let's do example 3. A standard die is rolled 200 times. Approximately how many times would you expect it to land on the number 5? You know, to get a 5, the probability of 5 is 1 out of 6. Approximately, you expect it to come up 1 out of 6 times 200 rolls. Theoretically, this is obviously. Yep. Any questions? All right. I think we'll move on. These are pretty straightforward. All right. Like we were saying, and is times, or is plus. So consider the experiment of rolling 2 dice. The probability of rolling a 3 on both dice. That means you have to get a 3 on the first die and a 3 on the second die. Right? A 3 on the first die and a 3 on the second die. So the second roll depends on the first roll, which means it will be a multiplying. It depends. It's dependent. So that's a multiply and a multiply. 1 out of 6 times 1 out of 6, 1 out of 36. This shows that out of possible 36 outcomes, only 1 outcome is favorable. The probability of rolling a 3 on either die. So that means getting a 3 on the first die or a 3 on the second die. See how important that is? A 3 on the first or a 3 on the second. So if it's on either, that's 1 out of 6 plus 1 out of 6, which is 2 out of 6, 2 out of 6, which is 1 out of 3. This shows that out of a possible 36 outcomes, 12, instead of doing 12 out of 36, I'm sure 1 out of 3 is a lot easier. All right. Any questions? Good. Good, 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 good. Then we've got complementary events. Complementary events are the opposite. So a complementary event is when the opposite occurs. For example, the complement to picking a red card in a deck of cards, selecting a black card, or not selecting a red card. So you can't always just say opposite. Sometimes you might have to just say the not selecting a red card. To find the probability of a complementary event, you can simply use the following formula. It's the probability of the event does not occur is equal to 1 minus the probability that it does occur. These are pretty straightforward. You know, the probability of it raining is 50%, not raining is 50%. Having a vanilla ice cream is 20%, not having a vanilla ice cream is 80%. Pretty straightforward stuff. It is useful for the harder questions. The way we represent it is probability of the event not occurring. So when you've got a line on the top, it means the opposite, so complementary, equals 1 minus the probability of the event. Okay. Any questions at this stage? Okay, so watch this. A card is chosen at random from a standard deck of cards. What is the probability that the card is not a black 3? So probability of not black, black 3 is equal to 1 minus probability of black 3. Well, how many black 3s do you have? You've got 2 black 3s out of 52. And then whatever that gives you. Does that make sense, you guys? Which is 50 out of 52, and then you simplify. Any questions? Am I going too fast? No, didn't think so. All right. Mutually and non-mutually exclusive events. Mutually exclusive events are events that cannot both occur at the same time. One result has no bearing on the probability of another result. For example, on a die, if you want to roll a 1 or a 4, the probability of rolling the 1 has no impact on the probability on rolling the 4. Therefore, since this is an or statement, we can just add the probability of rolling a 1 with the probability of rolling a 4. However, if you want to roll a 2 or an even number, we are faced with the problem of a result doubling up, right? Because 2 is an even number. So you can't just go, okay, probability of a 2, 1 out of 6, probability of an even, a half. Problem is, you've already included the 2 in here. So when the probability of 2 events is requested and some of those elements overlap, then we can find the probability of that event by taking the sum of the probabilities, just like we just did here, and then subtracting the overlapping events. Oh, that's obvious, isn't it? So a 6 plus a half minus a half times a 6. So that's a good formula to remember. If there is ever an overlap, it's the probability of A or B, which equals the probability of A plus B minus the probability of A and B. Any questions? That was a good example. Yeah, tell me. Sometimes
it's a bit confusing.
Sometimes theory is confusing, isn't it?
Yes.
I think once you actually look at the questions, you'll realize, oh, okay. Fair enough. But is this the only one you're saying is confusing? Just this one? Or Even this stuff.
Yeah, just the events that overlap.
Yeah, just yeah. That's fine. Watch this. So here, a coin is tossed 3 times. What is the sample space? The sample space would be heads. The coin is tossed 3 times. So you could have got a head, 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 tail, head, tail, head, head, tail, tail. And I think that's it. And then you could have got a tail, 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 head, head, tail, head, tail, 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 head. Find the probability of tossing an odd number of tails. Well, in this case, if you've already listed the sample space, you'll just go odd number of tails. Well, that's 1, 2, 3, 3. 3 out of 8. Will you use this formula? You will see. You're not going to use it as much as you might think about the overlapping events, because most of the times you're just going to do questions like this. Like I said, theory sometimes not as important as your practicals. But let's keep going and we'll see. Here, this could be one. When rolling a die, what is the probability of tossing an even number or a square number? Well, this is what I would personally do, right? I would go 1, 2, 3, 4, 5, 6. Probability of even or a squared number. Squared number. Okay, equals. For an even, you would say it's 2, 4, 6, which is a half, plus the squared number, which is only 1, don't forget 1, 1 and 4, which is 2 out of 6. But can you see how you overlapped with the 4? You've got to take that out. The overlap. So you've got a minus a half times 2 over 6. Yeah?
Okay.
Okay. Now, do you agree with that firstly?
Yes.
That's the formula, but you didn't have to. For some students, they just who they might not just understand this logical probability in more of a logical way. They'll just go, okay, wait, that's a half plus 2 over 6, but then there's just an overlap of the 4, right? Well, just take that 1 out of 6 out. Does that make sense? So Sam personally does this one. I don't really follow these formulas, but I've got to teach you because that's kind of important as well for some students who like to think of it like that. So I personally do it the bottom way, but some students like to do it the top way.
Okay.
So this one, it's up to you. Which one do you feel like is you? That's what you got. That's what you've got to look at. Am I a person that's just going to learn whenever there's an overlap, I add them and then take away them multiplied? Or me, what I do, I just go, okay, add, then what was the one thing that overlapped? Oh, it's this one. We'll just take that extra bit out, minus the 1, 4 out of 6. Same answer. Which one's you? Eden, what do you think? Lysandra, what do you think?
I think the first one for me.
Okay, there you go.
Yeah, probably the same thing, yeah.
Yeah. Is Tiana here yet? Tiana here?
No.
No. All right. All good. So yeah, I thought so. Most students do pick the first one. So it's up to you. Venn diagrams, let's go. A Venn diagram can be used clearly to categorize the results of an experiment, identifying any overlapping events. So this bag is filled with marbles labeled 1 to 10. Oh, I'm not going to show this. I think you guys get Venn diagrams right. This is overlapping. This is A only. This is B only. This is not included in A and B. So I think the best thing is just to look at questions. We'll have to come back to set notation. I'd rather do a quick Venn diagram before I confuse you with all this stuff. So let's find one. If we have one. That's it. Wow, they don't ask Venn diagrams in the HSC. Maybe because like so U9 and U10 based. I'm sure we can get one for you later on. That's not a problem then. No Venn diagrams. They're not that as important. Maybe because they're too easy. Set notation. Set notation is an older notation for probability statements. It doesn't come up that often anymore, but just in case. So the intersection, the idea is the intersection of a set is the fancy way of making an and probability statement. So if I was to say the probability of an A intersection with a B, you might have seen this in your functions topic. That's just the same as saying P of A times P of B. That's an and. And if you have a union question like this, so probability of A union B, it just means or. So they're mutually exclusive. So that's the probability of getting an A or a probability of getting a B. And if they're not mutually exclusive, that means there's an overlap. You do what we just did above. So if you ever see these, that just means and or intersection, union, and this means or. So I think you should write that so you don't get that confused. If you ever do see it, it just means and this one means or. So add, multiply, overlap. Okay, any questions? Move on. Okay. A quick way to find the total number, for example, if you wanted to find, yeah, that's just nothing. Tree diagrams. A tree diagram is a useful way to list all the outcomes of a multi-stage event where all outcomes are equally likely, and multi-stage event consists of two or more events occurring together. Here's an example. First coin, second coin, third coin. Right, so this is first event, second event, third event. Think of it like that. So your first event, you could have got a head or a tail. Then your second event, you could have got a head or a tail. In your third event, you could have got a head or a tail for each outcome. And that's pretty much how this works. And then outcomes are just, they're read like this: H, 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 T, H, T, H, H, T, 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 H, H, blah, 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 blah. Any questions about this? Nope. All right, and then you've got probability tree diagrams, which means that they could have different weightings. So the probability of a black or blue ball or whatever this would be, so that let's just say there was 3 blacks and 4 white in a bag. That means the probability of getting a black is 3 out of 7. The probability of getting a white is 4 out of 7. Now imagine you did get a black ball. So there was 3 blacks and 4 whites. Imagine you've already got a black. Well, how many blacks would be left? Wait, what happened here? 3 white, 6 black. Oh, in bag 2. Sorry, so that's a bit different. That's a bit different. 4 white. 4 white, 5 blacks. Yeah, no. Don't worry. Ignore this. Hold on. Let's just do questions. It'll be a lot easier. Let's go. Here we go. All right. A 6-sided die is biased. So the number 3 occurs twice as often as any other number. A 6-sided die is biased. So the number 3 occurs twice as often as any other number. Right? So again, think of it like this. You've got 1, 2, 3, 4, 5, 6. The number 3 occurs twice as often as any of the other numbers. So this is 2 times more likely to occur than it is these ones here. So it's not even. It's not 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6. Does anyone feel like they know what it is out of? If this is twice as more likely than it is these ones.
out of 9, I want to say.
You would say 9.
Yeah.
Let's think. Let's see. So that means this is what, 2 out of 9, and then this is 1 out of 9, 1 out of 9. That's your logic, right?
Yeah.
Let's see if it adds up to 9. 2, 3, 4, 5, 6, 7. It won't work. It's not 9 out of 9. So what is it out of, you reckon, now?
7.
Yeah, done. And see, I'm okay with making mistakes. I hope that you guys see what I do when I teach you. I teach you like the way you would. I hope for you guys to attempt this question in your exam. It's okay. You guessed 9. You tried it out. Oh, you realize, oh crap, yeah, it's meant to be 7. It's fine. Easy fix. You know why 7 also makes sense? Lysandra, think of it as, if it's twice as likely, think of it like that. That means there was 2 of them. If there's 2 of them, then you all of a sudden got 7 numbers. Something like that, if that helps. But yeah, this would make a lot of sense now. 2 out of 7. And you know what? Look at this. So how many different ways there is of getting the same answer? Good. All right, twice as often. The die is rolled once. Show the probability that an odd number occurs is 4 out of 7. Okay. Probability of an odd equals 1 out of 7, 2 out of 7, 1 out of 7. So 1 out of 7 plus 2 out of 7 plus 1 out of 7, which equals, because it's 1 or 3 or 5, right? It's not 1 and 3 and 5. It's 1 or 3 or 5. That's an odd number if you're going to roll it once. So you're adding. Does that make sense? Yeah?
Yep.
And you can, and again, see, you need questions. The theory doesn't really help. The theory is not going to teach you to do that 1 out of 7. You guys got to understand that with probability, and that's why I just wanted to rush through the theory real quick to revise some of the stuff you might have seen last year, whatever. But it's more questions. You just got to do questions. If the biased die is rolled twice, find the probability of the sum of the uppermost numbers being 6. Okay. If it's rolled twice, I would think of it something like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. To get a 6, it should have been this one here, 1 and 5. It could have been a 2 and a 4. Could have been a 3 and a 3. Could have been a 4 and a 2. Could have been a 5 and a 1. There's no other way you're going to get a 6. We agree with that? So the probability of a 1 and a 5, probability of 1 and 5, just so we understand this, is 1 out of 7 times 1 out of 7, which is 1 out of 49. Do we understand that? Probability of 2 and a 4. 2 and 4 is 1 out of 7 times 1 out of 7, which equals 1 out of 49. And then obviously you guys know probability of 4 and a 2 times it by 2 times it by 2. Yes, for these ones.
What about the
Yeah, I'm about to do that one now. The 3, right? Is that what you're saying?
Yeah.
Yeah, so probability of 3 and the 3. You tell me. What are you going to say?
2 over 7 times 2 over 7.
Of course. 4 over 49. And then what are you going to do to each one? Or what are you going to do to all these, obviously? You're going to add the different events up. Because it's this, or this, or this, or this, or this. So, yeah. Your answer is what? 2, 4, 8. I think the answer is answer 8 out of 49. Yes, these are all HSC questions, of course. Yep. Any questions, you guys?
No.
Josh, you're okay? Oh, yeah, tell me, Eden.
No, no questions.
Josh, all good as well? I think you were doing this at school, so it's probably a bit easier for you. Triple A. This biased die is now rolled together with two fair six-sided dice. All right, so this biased die is now rolled together with two fair-sided dice. Okay, together. All right. What is the probability that at least two odd numbers are uppermost? All right. This biased die, so one biased die is now rolled together with two fair six dice. So how many dice altogether? We've got three, right? Just one biased die and another two, so that's three. Three dice. We've got one, let's say one biased and two normal. What is it probably that at least two odd numbers are uppermost? Two odd numbers are uppermost, so that means 1 and a 1, at least two odd numbers. Because you could have got three odd numbers. You could have got 1, 1, and a 1. Okay, all right. So you could have got a 1, 1, and then an even number. All right. I know how I would do it, but is it the quickest way? Let me have a quick look. Yep, it is the quickest way. Odd, odd, even. Can't do anything. Let's do it. So three dice, one biased, two normal, one biased, two normal. All right, so it's going to be like this. So you need to have, what did I say? At least two odd numbers, right, you guys? So that means it's going to be from the, let's say, it's going to look like this. Odd, odd, even. It's going to be odd. So this is biased, normal, normal. Odd, odd, even, odd. Odd, odd, odd. And it could have been even, odd, odd. Did I miss anything, you guys? Odd, odd, and then it could have been, yep, that's the same. That's the same. Odd, odd, even. Okay. Odd, odd, even. Let's make sure. Odd, even, odd. Yep. Odd, odd, odd. Yes, and then even, odd, odd. Okay. And I hope you guys are seeing, look at my working out, my setting out. So I hope when you're learning this as well, that's cool. You go, yep, theory, absolutely crap. Once you know adding and multiplying, and is multiplying, I mean, and or is plus, I mean, that's it. That's all you can do with that. You got to start applying to the questions. So you're setting out, look at the way I'm setting out. That's something you've got to learn. That's a skill. It's not really part of the math. It's a skill that you've got to learn to set out. So that's my logic. And now if I'm trying to get an odd, to get an odd, I think we've already worked out the probability of an odd number is 4 out of 7. True, in I. So if it's biased, 4 out of 7. 4 out of 7 times odd in the normal one. Odd in the normal one will just be half because it's normal. So a half times even, which is a half, plus odd, which is 4 out of 7. I think you guys get what I'm about to do. Half times a half, plus 4 out of 7 times a half times a half. So you could have just times it by 3 if you had realized that, but we'll continue. And then even, 3 out of 7 times a half times a half. And that's it. So talk to me now. What do you reckon, Eden, Lissandro?
It's
It's
very
all
long.
right.
Yeah, it's just very
Mhm.
tedious.
Yeah, and that's how these are going to be. So that's it. I can't make it any simpler. You're going to look at your textbook questions, they're going to be straightforward. But the truth is your exam questions are going to look exactly like this. The setting out's super important. You know, you're not meant to, it's not like calculus, let's say, where you're going, oh yeah, y equals x squared, what's y dash? Oh, okay, 2x. It's not like that. Probability is a little bit more like, okay, what are you saying? Let me draw it out. Let me act it out. Let me write it. Let me list it. Let me I don't know, work backwards, whatever the idea is, and then the answer is the easy bit. I mean, this bit here is so simple once you know what is happening. So you can see I did it slowly. I broke it down, tried to understand what's happening, and yeah. And then obviously then just plug it into your calculator. All right. All right. All right, let's do it again. Let's do it again. Nicole and Mariana play against each other in the third round of the Australian Open. In this tournament, the first player to win 2 sets wins the match. The probability that Nicole wins any set is 70%. So Nicole wins is 70%. Nicole loses 30%. Find the probability that the game will last 2 sets only. So Nicole and Mariana play against each other in the third round of the Australian Open. In this tournament, the first player to win 2 sets wins the match. Find the probability that the game will last 2 sets only. That means in I, Nicole must win the first one and Nicole win the second one. Or what? Or what? Eden? Nicole win the first, Nicole win the second, or
Mm.
Come on.
Nicole loses.
say it again? Yeah, which means Mariana win the first one, Mariana win the second one.
Yeah.
Right? Don't overthink it. Trust me. Just do what I keep saying. Act it out. And that's the biggest word I can say for probability. Play around with it and like actually act it out. Yeah, you know it. Nicole, or so Nicole winning is 70%. The first one times 70%. The next one plus Mariana winning, which means Nicole loses. What's the probability of Nicole losing?
30%.
Bang, bang. And then that's the answer that you're looking for. Yeah? Any questions, you guys? Find the probability that Nicole wins the match. For Nicole to win the match, what could happen? Come on, tell me. Do you watch tennis? Lissandra, do you watch tennis, for example?
No,
No, so you don't know how it works at all?
like I know like the point system, but yeah,
But like, do you know, for example, okay, so for Nicole to win the match, and there's only 2 sets to win the match,
yeah,
right? So it could have been Nicole, obviously,
yeah.
or what could have also happened?
It could have been Mariana, or Mariana Nicole, or Nicole Mariana.
No, not exactly. Look what you just said. Mariana, Nicole, Mariana, Nicole, whatever. Yeah, that doesn't mean Nicole won, because that's still only, you've only won one, you've only won one. She won one. Does that make sense?
Yeah.
So you're close. You're very, very close. This one, absolutely no, because that means Mariana wins.
Okay.
That's incorrect. You want to try it one more time? It is Nicole, Mariana, and
Mariana Nicole.
no.
Nicole.
And Nicole.
Yeah, Nicole after that. So see, I won the first set. You won the second set. What happens between you and me?
Tie.
We got to play a third set. Yeah, exactly. And then the third set, Nicole needs to win. Or Mariana wins the first one, and then Nicole,
wins.
Nicole. That's it. That's the only possible options. Do you get that now?
Yeah.
And then, of course, the math is easy. So 0.7 squared plus 0.7 times 0.3 times 0.7 plus 0.3 times 0.7 squared, because that times that is 0.7 squared. And then you get an answer. What do you reckon, you guys? That's okay? Now,
Yep.
find the probability that Mariana wins the match. Well, okay. What are we going to do? Are you going to do it all again? You can do the above again, again, or what? Come on, think about it. The probability that Mariana wins the match. If you now know the answer for Nicole, what could you do? Eden, give me a guess.
Um,
Oh, yes.
is it just Mariana times Mariana?
No, because it works the same way, right? You could do the above
Oh,
again, like
just
Mar-
the
yeah,
Mariana, then Nicole,
that's
Mariana,
what I'm saying. You
Mariana.
could do that. You could do. That's what I meant by you could do the above again. You can do the above again for, maybe I should write it for Mariana.
Uh,
Or I want
Mariana
the
can win twice, and Nicole can only win once or less.
yeah, correct. Which is exactly what you guys are saying. This is double I. So you can do the above again. So just like, look, you guys could say that, or this, or this. So I agree. This could happen. That's not a problem. You'll get the answer. Or think about it. Think about it. I'm trying to say another version. Think about what you've just done here. Maybe Josh. Josh, any ideas? And don't straight away just say no as well. Think about it, you guys, because I feel like you can do it. Because when I'm going to say the answer, you're going to be like, oh, really?
Can't we just put the same answer down?
No, it's not really going. Well, is it? Is it like here? Was Nicole the same as Mariana winning?
Oh,
Man, I'm overthinking.
oh, wait. Oh, wait. I was gonna say
Oh,
like
what if I said this? Oh, yes, go. Just say it. Just say what you're going to
like
say.
how Nicole is winning, then we do it.
Yes.
Nicole not winning.
Yes. Bingo. Absolutely correct. That's why it's worth a mark. Because it's exactly the same. So, if Eden, if you win, if your probability of you winning is 80%, what's the probability of me winning? 20%. So you could always do that. So keep your complementary events in mind. So yes, you could have done that, or you could have just said probability of Mariana winning equals 1 minus your answer in double I. Double I. Whatever that would be the color. Which is again simple. The Sandro makes sense, doesn't it?
Yeah.
So you guys were doing the opposites, and like, I mean, you could do the math and it all works out. That's not a problem, but yeah, you know that makes sense. Mariana winning means Nicole loses, so not winning. It's the same math, same logic, but yeah. All right, good. Let's try. Maybe I'll leave that one for homework, let's say, so you guys can think about it. Let's try this one, since it doesn't have any parts. All right. As part of their strategy to reduce road accidents, police are using 3 different independent methods to detect speeding motorists on a freeway. The probability that a speeding motorist will be detected by a highway patrol officer is a third. by fixed camera is 3/4, and by mobile radar unit is 1/2. The first thing you'll check is, do these things add up to 1? And of course they don't. Right? They're more than a 1. Calculate the probability that speeding motorists will be detected. So the speeding motorists will be detected by a highway patrol officer is 1/3, by fixed camera is 3/4, and by mobile radar unit is 1/2. Calculate the probability that speeding motorists will be detected. Will be detected. Police are using 3 different independent statistics for speeding motorists. The probability that a speeding motorist will be detected by a highway patrol officer is 1/3, 3/4, and then by mobile radar unit is 1/2, which means not by a mobile radar unit is 1/2, not by a fixed camera is 1/4, 75% chance of multiplying will be detected. This, but multiplying means this and this and this. And there's my question. The probability that a speeding motorist will be detected by a highway patrol officer is 1/3. Let me think about this. What are we doing here? Calculate the probability that a speeding motorist will be detected. That a speeding motorist will be detected, because there's overlap. There's overlap. Speeding motorists will be detected.
How is the overlap?
Say it again.
How is the overlap?
See, because they could get detected by a highway patrol officer and the fixed camera at the same time.
Okay.
Does that make sense?
Yeah.
Yeah. And plus, there's overlap, because if I add these, 1/2 plus 3/4 plus 1/3, you know it's greater than 1. Does that make sense? So my answer would have been 1/3 plus 3/4 plus 1/2 minus 1/3 times 3/4 times 1/2. Let me just see if the math works out. No, it doesn't work out. No, wait, what am I missing? What am I missing here? Detected is, oh, I really overthought that then. Okay, all good. All good, all good. All right. Probably that experiments will be detected, but that doesn't make sense. I think there's a typo. Yeah, then that must be a typo. They must have done a mistake. No, actually it does. It's right. It is right. Probability of getting detected equals 1 minus the probability of not detected, which equals to 1 minus 1/3 times 3/4 times 1/2. Sorry. 2/3 times 1/4 times 1/2. And then that should give us the answer, right? Yeah, 11 out of 12. So probability of not being detected is 2/3 times 1/4 times 1/2. But then that means I could have just done this, right? 1/3 times 3/4, which is what I first thought. But I thought, oh, that's too easy. No, it doesn't work. It's so interesting. Such an interesting question. Fair enough. Very, very interesting. All right. I guess, yeah, when, I don't know, I don't even know what part of probability this is, but it looks like when these are larger than 1, you're doing the complementary event case. So probability of detected is equal to 1 minus the probability of it not detected. 2/3, a quarter, a half, 1 minus that, 11 out of 12. I wonder why you can't go 1/3 times 3/4 times a half, because that would be the probability of being this and this and this. Very interesting. Whereas this is the probability of not detected by this and not detected by this and not detected by this. Yeah, that's smart. That is really smart. So, wait, do you guys understand the logic of this? And how this is working from what I was just talking about?
Kind of.
Kind of. So I'll say it again. Look, so if you just did probability of, if you just went and did 1/3 times 3/4 times a half, right? That's the probability of highway and fixed camera and mobile radar unit, which, yeah, doesn't make sense. You're not going to get caught by all three at the same time for speeding. So that's just, the math of that doesn't make sense. What's the probability of you being detected? Well, think of it like this. So not getting detected, so not by a police officer, is 2/3, right? And not by a fixed camera is a quarter. And then obviously not by a mobile radar unit is a half. So for you to get caught, that means you had to, I guess, avoid the highway patrol, and the fixed camera, and the mobile radar unit. So you had to avoid the highway, which means you had to not get detected here, which is 2/3, and you had to avoid this guy, which is a quarter, and you have to avoid this, which is a half. And that's how the math of this is working. Really interesting. I would actually put this into a, like if you had a exam book or something for your topics, that would be one thing I would put in probability, because that's a really interesting question. All right. Let's maybe do a HSC question, 2 HSC questions, and then I'll leave that one. Sounds good. Let's do it. Let's do those two. We'll leave that one for next week as revision. That's good. Let's just start with this one and we'll come back up. All right. A pack of 52 cards consists of 4 suits, 13 cards in each suit. 1 card is drawn from the pack and kept on the table. A second card is drawn, which means there's 51 left. Keep that in mind. And placed beside it on the table. What is the probability that the second card is from a different suit to the first? Okay. What is the probability that the second card is from a different suit to the first? That means, all right, let's think about this. Again, play the game. There's 52 cards. 1 mark, huh? There's 52 cards. So it's for the second card is from a different suit. For it to be from a different suit, you've got to take out all. Okay, all right. Go play the game, like I said. So tell me, Eden. Let's start the game. 1 card is drawn from the pack and kept on the table. Tell me the card. Tell me the card. Seriously.
Any card?
Say it again.
Any card?
Yeah, any card. Yeah, any card. Play
5
the game.
spades.
5 spades. That's it. 5 spades. It's on the table. It's finished. A second card is drawn. So how many cards do you have left?
50.
50 what? 1.
What?
Yeah,
Oh,
51,
51.
right? And placed beside it on the table. Sorry. What is the probability that the second card is from a different suit to the first? So you have 51 cards. How many of these are there?
4.
Ah,
Wait.
no.
13.
How many spades? Yeah, there's 13 spades. So you've already taken out 1. So how many, well, I mean, you could say, maybe I'm complicating it. I was going to say you could take out 12 from 51, or I'll rather just say, how many other suits are there? How many other cards with different suits are there?
3. Oh, wait, no.
No, how many other cards with different suits? There will be 39, right? There's
Yeah.
13, 13, 13. Does that make sense? Or what you could have done, if you know you've already taken out 1 of the spades, so there's 12 spades left. Spades left. 51, take away 12 is also 39. 39 other cards. Does that make sense?
Yes.
See how I played the game? Can you please do that for your questions? You've got to play the game. Sometimes it's just a bit easier to see. Double I. The 2 cards are replaced. The 2 cards are replaced and the pack shuffled. 4 cards are chosen from the pack and placed side by side on the table. What is the probability that these 4 cards are all from different suits? 4 cards are chosen from the pack and placed side by side on the table. 4 cards are chosen from the pack. That means the first one had to be, but it's just 4 cards, right? It's not doing it one at a time.
I'd say 1 on 16.
1 on 16. 1 on 16. How'd you get that? 4 out of 52 or something? No.
Yeah.
Yeah? Something like that? No.
Yeah. And you pick them all at the same time. So. Well,
Yeah, so 4 cards. Let me think about it one more time. 4 cards are chosen from the pack. So we've got 52. We're choosing 4 cards. So you just go bang, 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 bang. It's saying and play side by side. So there they are. And what is the probability that these 4 cards are all from different suits? That feels a bit like combinations. So this has to be a heart. This has to be a diamond. This got to be a spades. This got to be a clubs. To get a heart, you've got 13 times 13 are all from different suits. 13 out of 52. 1 out of 4 times 1 out of 4 times 1 out of 4 times 1 out of 4. Maybe. I think so. 1 out of 4. Because to get ahead, it's 13 heads out of 52, and then 13. So 1 out of 4 to the power of 4. But sounds weird to me. Probably there were 4 cards, all different suits. Doesn't matter. Times. You can't choose that. Times 2 swords left. The problem with that, it doesn't say to do that. It just says 4 cards are chosen from the pack. It doesn't say you're going to place one down. That was very bad. It doesn't say that. As if you guys become this ambiguous. Alright. See, the way I was thinking about it is you're choosing 4. But it looks like you're not choosing 4. What you're doing, you're choosing 1. Then you're choosing another one. Then you're choosing another one. Then you're choosing another one. Just like you were in I. Unfortunately, it doesn't say to do that, but what can I do? All right. Well, that changes everything. So to get ahead, it doesn't really matter. You choose anything. So 52 out of 52. You're choosing one of them. So that's gone. Then you've got 3 suits left, which means you've got 39 suits out of 51 suits left. 51 cards left, sorry. 39 out of 51 cards left. Do we understand that? Because you've only chosen the one card here. It doesn't matter what that card is, like I did here. It doesn't matter what the card is. Then you've got 26 suits left. You've got 50 cards. And then, of course, you've got 13 suits out of 49 cards. So it's not hard. The problem was I didn't read it like that. And I don't know if you guys did or not. But the way I read, 4 cards are chosen from the pack and placed side by side on the table. It's as if you're picking 4 cards. And picking 4 cards is different to picking 1 card at a time. Because if you pick 1 card at a time, it works like this. But if you pick 4 cards together, then that changes things up. But so 4 cards at a time, the answer would have been this, which is what I had. But oh well, what can you do now? Annoying. Bloody advanced math. Hate the words here. All right, all good. Annoying. You can see how I feel about this. Whatever. Let's do another one. And let's get another one wrong. Chris has 4 pairs of socks in a drawer. Each pair a different color. So 4 pairs of socks. That means 8 socks altogether. 8 socks altogether. All right. He selects socks 1 at a time. There we go. That's better. He selects socks 1 at a time and at random from the drawer. The probability that he does not have a matching pair after selecting the second sock is 6 out of 7. Explain why this is so. The probability that he does not have a matching pair after selecting the second sock is 6 out of 7. So there's 8 socks, and there's obviously 4 of them, 4 different colors, let's say. That he does not have a matching pair after selecting the second sock. So first sock, let's call it blue. That means there are 7 socks left. So the second sock, let's call it red, right? And then third sock, probably does not have a matching pair after selecting that is okay, perfect. And then of course third sock can be anything else. Third sock, anything else, doesn't matter. Okay, so first sock is blue, so that would have been a 1 out of 8. How many socks are left? There are 7 socks left, and there's only 1 blue sock left. 1 blue sock left. 1 blue. So the probability of not selecting a matching pair, in other words, not selecting a blue in here in the second sock, is 1 minus 1 out of 7, which is 6 out of 7. So the probability of not selecting this will be, and you guys should know that, because how many socks are left? If he's chosen 1, he's chosen, there's 7 socks left. How many pairs of socks do you still have? You would have 3 different colored ones. You've got red, green, yellow, let's say. So that's 6 socks out of 7. You could have done that as well. Does that make sense? Yes. Double I. Find the probability that he does not have a matching pair after selecting the third sock. He does not have a matching pair after selecting the third sock. So that means it would have been black, would have been red, and then would have been green. So what's the probability of this occurring? So that means this had to be black, red, green. So you could have done it a few ways. This is, what did I say? This is 1 out of 7. 1 out of 8. Then there's this one here, which is 6 out of 7. Then this one here could be, it's not matching still. How many socks do you have left? You've got 6 socks left, and you would have 4 of either green or yellow. Does that make sense? Yes, no, maybe?
Little.
A little bit. So find the probability that he does not have a matching pair after selecting the third sock. So the first sock is anything. It doesn't make a difference, right? It doesn't matter. Like, it doesn't. He's selected something. It's done. All good. Then he's got to select another sock that's got to be anything but what do you call this? But blue. So how many socks can he pick from? He's still got 6 socks to pick from that are not blue, because there is one more blue that matches, and there's still 7 socks left. But now he's picked this color, whatever it is, it's red. So how many socks are left? Well, there'll be 6 socks left altogether. The 2 socks are either blue or red, and there's 4 socks that will be anything else, green and yellow, let's say. So the probability of him still not having a matching pair after selecting the third sock is 2/3. 4 out of 6. Sorry? Yeah? That makes sense?
Mm-hmm.
What is the probability that the first 3 socks include a matching pair? The first 3 socks include matching pair. That means it could have been blue, blue, and let's say green. Oh, but would you have gone to green if you already got blue and blue? The probability that the first 3 socks include a matching pair. No, I think you probably would have gone more blue, green, blue. Or you would have gone blue, green, green. That's it, pretty much. Because I'm assuming if you wouldn't have done this. If you've already got a matching pair, would you go out and get another green one? Why would you do that? So I'm going to use that logic, and I guess we'll find out. Blue. All right. So this. So this times this, because this is dependent on this. All right. So blue. Blue is 1 out of 8 times green. Green is 6 out of 7 times, because it doesn't matter which one it is, times the blue that we've got, that we definitely need, out of 6, plus 1 out of 8 times 6 out of 7 times, there's still 1 out of 6. 1 green left out of 6 socks left. And then you're just adding it up. Yeah. And then I'm actually thinking, oh yeah, that's it. Oh, times it by 4. 4 pairs of socks. No. That's it. 1 out of 8 times 6 out of 7 times 1 out of 6 plus 1 out of 8 times 6 out of 7. 6 different socks times, yeah, it doesn't matter which sock. Oh, times 4, because there's 4 different colors. I think so. All right, let's look. For matching pair. You get this one wrong as well. There's all this. Oof. I just do everything wrong. 6 out of 7. Wait, 6 out of 7. Yes. Double I. 6 out of 7 times 2/3. Not and not. Oh. Of course, what am I doing here? 6 out of 7 times, I don't know why I did pluses there. 6 out of 7 times 2/3. That should have been, of course. And then, wait, let me check this one. Probability of a matching pair. 1/7 plus 6 out of 7 times 2/6. 1/7 probability of a matching pair. 3 out of 7. Probability of a matching pair. So I would have not thought of it like that. I thought of it like this. Let's see if my math still works out. 6 over 7 times 1 out of 6 times 4 times 2. No, I got 1 out of 7. The answer is 3 out of 7. Matching pair. How is that one working? 1/7. So you can see the topic that I absolutely hate. What is the probability the first 3 socks include a matching pair? The first 3 socks include a matching pair. I would have still done it this way. First one could be, alright, let's do it again. 6 over 7 times 1 out of 6 times 2. No, this is right. This is right. Times 2. Just this extra 1 out of 7. Let me think of it again. What is the probability that the first 3 socks include a matching pair? Where are you guys getting that 1 out of 7 from? First 3 socks. Did they seriously do boy, boy, girl? Boy, blue, blue, green. Let's have a look. What is this? So this is 1 out of 7. Yeah, they did. They actually did do this case. Seriously? Why would you have chosen a green if you've already done this? 1 out of 7. That's exactly what they did, plus this. I can't believe they actually did that. Fair enough. Alright, I don't know what to say. The probability of the first 3 socks, including a matching pair, it looks like you would have to include the first 2 being a matching pair. But I guess my logic would have just said, but if you've already got your 2 socks, why would you have gone for the 3rd sock? But it looks like you've got to include that. And I just don't see why you would include that. That's weird. Who trusts these answers? Let's have a look. What year is this? Chris has 4 pairs of socks. Let's see if we can find an HSC question and confirm this is right. Because I don't know. This is just another teacher's solution, and I don't know if I trust it.